Okay, so if there are no questions, let's start. So last time we were looking at logistic regression, which is essentially a cousin of linear regression or a generalized version of linear regression. So remember, we started with linear regression where we said that y is our output and y is connected to your x through a link likelihood function which is normal. We assume that y is a normal distributed random variable with the mean as w transpose x and sigma square as the variance. Then we said that, hey, why just use normal distribution as that connector, right? Instead of that, we graduated to looking at Bernoulli distribution. So instead, hey, how about assuming that y is a Bernoulli distribution, where of course Bernoulli distribution only has one parameter, which is theta, which is a probability of heads, and that parameter could be a function of W transpose X, right? So in the case of linear regression, the mean is a function of W transpose X in the way that mean is equal to W transpose X. But here we can't use theta equal to W transpose X because theta is, we need theta to be between 0 and 1, right? Because the Bernoulli distribution, the theta parameter indicates a probability, which means it has to be between 0 and 1. So we did our usual trick. We applied a sigmoid to W transpose X, and we said that theta equal to that, right? So that gave us a new form of a regression model. And then what we saw was that we could use that theta to determine if the point X belongs to class 1 or class 0 by just saying, is it greater than 0.5 or less than 0.5, right? So if the probability, because theta is the probability, so if theta is greater than 0.5, which means that it is more likely to be class 1, so we assign it a probability of class 1. However, another benefit that, now one thing that I think somebody here pointed last week was that that threshold is equivalent to saying W transpose X is greater than 0, right? So, and we can quickly look at that. So the decision function for logistic regression is theta greater than 0.5 or is because 1 over 1 is this greater than 0.5, right? And if you sort of rearrange it, if I bring this here, then open it up, what it will show you, or we can do that, right? So I can write it as half, bring that 2 here. So essentially, it says that 2 is greater than 1 plus exp minus W transpose X. I'm going to switch it around and move this here, and it means that exp minus W transpose X is less than 1, or if I take log on both sides, it's just W transpose X is minus W transpose X is less than 0, or W transpose X is greater than 0, right? So these are equivalent. So if once you have W, you can either apply this rule or you can apply this rule. It's the same thing, right? However, what you would remember is that this is same as using perceptron decision rule, right? In perceptron also, we had the same W, right? So what is the difference between these two classifiers then? I mean, both of them are doing the same thing for a new test data point. There are two differences. The first difference is that perceptron gives you a decision. It says, is this object class 1 or class 2, right? So if it is greater than 0, I say it's class 1, and if less than 0, class 2. But logistic regression gives you a probability, which you can use later on, right? So it tells you how confident is my classifier in calling this class 1. So in your gradients quiz last night, you must have seen that, right? So a good classifier is one in which the decision is 0.9, 0.95, closer to 1, because then you have very good confidence that the point is that in logistic regression, if your theta, right, which is just this, is equal to 0.9, or if theta is equal to 0.6, both of them means that you will predict that class to be 1, right, because greater than 0.5. But this is much better than this, because here you are really confident that your probability is closer to 1, right? Ideally you want it to be 1, but in real life It might not be 1, but if it's closer to 1, then it's better. So that's one benefit of logistic regression, is that it gives you something more than just a prediction, just a classification. Okay? So that is one. But the second and the most important difference between logistic regression and perceptron is not how they do the decision, but how they learn the W, right? So the difference, the magic difference is in how W is learned from training data, right? So if you remember, in perceptrons, we used a squared loss function, right? In perceptrons, the loss function that we had, this is logistic regression. So in perceptron, the function was yi minus w transpose xi square summation over all I and maybe a half here, right? So this was our perceptron loss function, and then we optimized that. We found the w that minimizes this. In the case of logistic regression, we do a log likelihood, and our function looks like this. It is theta, so yi log of theta I plus 1 minus yi log of 1 minus theta I summation I equal to 1 through n, where theta I is equal to 1 over 1 plus exp minus w transpose xi, right? So what you see is that both of them have a loss function, which is a function of your w, and in both you do some kind of a gradient descent algorithm, but the loss functions are different, okay? And later on what we will see is that, so both of them, we call them linear models, because in both x is being combined linearly to get your final prediction, but in one of them the loss function is this, in one of them this is this, right? And it turns out that this loss function is a little better in finding a good w, okay? And later on we'll do some very informal analysis of these loss functions to see why they are better. Once I have also talked about another linear model next week or this week, and maybe a little bit of next week, which are support vector machines. So what you will see is that even support vector machines have the same decision rule. There is some w, you combine w with x, and then you see if it is greater than 0 or not, right? That is still the same. However, the difference is that how the w is learned, and in support vector machines is another way to learn w, and what we will see is that each one of them have certain properties. And for now, what all I want to say is that this loss function is sort of better than this in the way that it sort of leads to an optimal solution, okay? So that is why even now logistic regression is preferred over perceptrons. All right, any questions so far? Okay, and then we looked at how to learn, right? That is the part that we know, of course. So we can express our loss function, which is here, right? And then we can compute the gradient of that with respect to w, and this is the gradient. This actually should be gradient, and then we can do our update, right? And this is we are maximizing this. This is the likelihood, right? This is not loss. This is inverse of loss. So we want to maximize it, which means that we want to reach the peak of this error function, and to do that we need to move in the direction of the gradient, not in the opposite direction. That's why you'll see a positive sign here instead of negative, in which we saw in neural networks or perceptrons, where we were trying to minimize the loss, right? So that is easy. We can do that. Now, one thing I also started talking about was that, now this is orthogonal to this discussion, is that sometimes setting this eta is tricky, right? Eta is the learning rule, so that tells you how much you jump at every iteration. And instead of that, there are other ways to do this, right? So this is more a discussion on mathematical optimization, but I thought I'll just talk about it here. Is that if you want to make it better, right? Better in the sense it should reach the right answer, and it should also reach it fast, right? So essentially this. So I want to reach the top, and I want to reach it fast, right? So that is where setting eta becomes tricky, because if you set eta to be large, there is no guarantee you'll reach the top. You might jump over it. And if you set it too small, then you'll reach very slowly, right? And that's something that you have experienced with when we did neural network training, is that it takes a long time, right, for real functions. So another way to speed up convergence is to use this other second order method called Newton's method, where instead of just updating your W's in the direction of gradient, you also have another thing that is being multiplied here, which is the inverse of the Hessian. Okay, so Hessian is the second order derivative of your J with respect to your W, which is analogous to second order derivative, right? So if you use this, you can actually, then setting eta is not very important. You can set eta to 1 and that'll be fine. But this kind of controls how you jump at every step. And what you see here is that because this will change, right? So eta is fixed, but h of k, which is the Hessian of your j with respect to your weights, is going to change at every step, which means that at every step, you are going to jump in a different way, which is really cool, right? In eta, you were always going to jump. So this is kind of adaptive. It adapts to the nature of the surface and then reaches to the top. Another thing that you'll see here is that when we were doing eta, just eta in our here, when we're just doing eta, then let's say W has 4 elements in it, right? W is 4-dimensional. Then for each, when you're updating each one of them, this is a vector, right? So each entry in this is going to be incremented by eta, right? Which means that you are going to make a jump which is equal in all directions. However, when you use this, there is no guarantee that it will be a same amount of jump. It depends on what your inverse of Hessian is, which means that maybe in certain dimension, right? So let's say your W has 2 elements, W1 and W2, 2-dimensional vector. Maybe in W1, you might have already reached the optimal point. So then you do not want to jump anymore. Whereas in W2, you still might want to jump. So h of k would sort of allow you to do that. So that is why the convergence here is faster and it's more accurate, even if you don't use a good value of eta. Okay, any questions? All right, so in the third programming assignment, which will be out next Monday, is going to be mostly about logistic regression, right? So in that, you will have to, I don't remember. I guess you'll have to do both. One is just simple gradient descent, and maybe for extra credit, you have to do this Newton's method. I'll let you know, but just pay a little more attention to this. Okay, so that's it, right? So for logistic regression, the Hessian is given like this, right? So it's easy to compute. It's not like it's a terrible thing. So so this is essentially, you're just taking your current output theta I, 1 is theta I, and then multiplying each one of your input vectors. So this is like a second order multiplication. It will give you a d by d matrix, and then you're just adding them all together. So that gives you a Hessian, and then you can sort of update it using your Newton's algorithm. All right. Now another thing is more of our normal discussion is that what if we want to regularize this, right? Remember in last time we saw that in linear regression, if we do not regularize, it leads to overfitting, right? And before that, another thing is that even in logistic regression, if you want to learn nonlinear boundaries, you can do basis function expansion, just like we did in linear regression. However, if you want to control the complexity of your boundary, you can do regularization. So one of them is, of course, similar to ridge regression. So we can call this like ridge logistic regression, but we don't really call it that. We call it just L2 regularized logistic regression, because we are applying a L2 norm to it, and then we are working with it. And it turns out that solving this is still easy, because your new function, your new job function, new objective function is your old one, which was your likelihood, log likelihood, and then a penalty term, which is the L2 term. Now here there's a negative sign because we are going to maximize this, that's all, right? So if you want to apply gradient descent to that, you want to compute the gradient, which is still easy because you can compute the gradient of this part, and this part's gradient will just be lambda w, which is similar to what you did for your ridge regression. And even the Hessian is easy to compute. The Hessian is whatever Hessian of this part minus lambda I, because you're going to take derivative of this component with respect to w again, right? So it's like taking d by dx of x, that's 1. So here, since w is a matrix, is a vector, the d by dw of w will just be an identity matrix. It will just be all ones on the diagonal, right? So it's easy. So which means that you can do this regularized logistic regression either using Newton's method or using simple gradient descent, and it should work. Okay. Somebody could ask that what if we want to apply a L1 penalty like lasso, right? Instead of having an L2 norm here, what if I just had lambda mod of W? And yes, you can do that, and there are ways to do that as well. In fact, one of my PhD students is right now sort of doing research on how to do it more efficiently. It's not a very easy problem to solve, so Ji Liang works on that, but there are ways to do that as well. All right. Any questions so far? Okay, so there are two topics I want to talk about logistic regression today, and then we'll move to the support vector machines, all right? So one thing is, what if we want to handle multiple classes? In fact, somebody had a post on gradients as well, is what if instead of two classes, like 0 or 1, if I have k classes, okay? Answer is you can still do it with logistic regression, but it becomes what we call multinomial logistic regression. The one before that is called binomial logistic regression or binary logistic regression. But when you have k classes, now you're working with a multinomial logistic regression. So here is the idea. So clearly when you think about multiple classes, right, we think about multi-Newly distribution, because multi-Newly distribution is the generalization of Bernoulli to multiple classes, right? So Bernoulli is if you're trying to model a toss of a coin, and multi-Newly is if you're modeling a roll of a dice, right, k-sided dice. So in Bernoulli, the parameter is theta, right, and theta is a scalar which lies between 0 and 1. However, in multi-Newly, we have a parameter which is, I can still write it as like a uppercase theta, which is actually a vector with k elements, and each theta of a small k is between 0 and 1, right? Because now you want the probability of each class. Earlier you had only two classes, so you just said what is the probability of class 1, and then we said probability of class 2 is just 1 minus of that, right? But here, since you have k possibilities, so you need k probabilities, right? So what we do now is, if you want to model y, which can take k values, right, not just 2, so then we say that y is multi-Newly, okay, with some theta, because it has only one vector, and this should be a function of x, function of w and x's, right? So w transpose x, because we want it to be a linear model, right? So earlier, because we just had one theta, which was a number, we just said this is 1 plus sigmoid of w transpose x, but now we need a vector. So what we do here is that we say that y is multi-Newly with a vector, and each entry here is exp. So now instead of one weight vector, we'll have k weight vectors, right? So we'll have w1 transpose x over the summation exp. I'll not write it that way. So we say y is multi-Newly with this theta. I'm going to just expand it. It will be theta 1, theta 2, theta k, right, where each theta k is equal to exp wk transpose x over summation k equal to 1 through uppercase k. All right, so all we are saying is that instead of, well, actually let's write it just theta j, so the jth entry will just be exp of wj transpose x divided by summation of r, right? So what this denominator will ensure is that each one of these thetas is a probability, because it will be between 0 and 1. So theta j will always be between 0 and 1. So it's a probability, which means that we can model Y as a multinull. All right, so this is how multi-class logistic regression is set up. So instead of just assuming one theta and assuming that theta is sigmoid of W transpose X, now we are going to assume that in our model we have k weight vectors, and then each probability is essentially exp of that divided by the sum. Okay, so that's the general idea. All right, any questions so far? So now so let's first look at the prediction rule, right? So what is the prediction rule? Which means that when I get a new x, how do I figure out which one is the large probability? It's very simple. You just compute p of y to be 1 given some x will be just exp w1 transpose x divided by this summation. Right, and then so on. So y equal to 2, y equal to, so probably y equal to the last one, k will be exp and since these all are probabilities, they'll all sum up to 1, right? So then what you do is you basically choose the highest value, right? You just say, okay, which one is the largest probability, and you say that is the class. So it's very similar to logistic regression, but in logistic regression we just computed y equal to 1, y equal to 0 was of course 1 minus of that, and then we chose whichever is the higher value, which means whichever is higher than 0.5 will be the class. So that is the idea. So this is also known as what we call softmax prediction, because we are not just taking the maximum value. For example, if you remember what we did in neural networks, right? In neural networks, if you had k output nodes, you would take the node that has the highest activation at the end, right? But these need not be between 0 and 1. So here what we are doing is we are first converting it into between 0 and 1, and then taking the highest value. So it's not only gives you a prediction, but also gives you a probability. The same arguments apply here as well. So if I get, let's say I had 3 classes, right? And if I get probabilities which are 0.3, 0.3, and 0.4, I will take the last one as my predicted class because that's 0.4. But that's not very good because it's very similar to other classes as well. Whereas if I get a distribution which says class 1 is 0.8, class 2 is 0.1, class 3 is 0.1, then it's a better prediction. So it's nice in that way, right? So that's why we call it softmax. Then another name that you might see in literature for logistic regression is max-ent classifier, which stands for maximum entropy classifier. And there's a reason for that, because it's kind of like you're maximizing the entropy of your classes. But that's something you don't have to worry about too much. But let's say you're reading a paper, you see that term, should not get confused. It's essentially another name for multi-class logistic regression. All right, any questions so far? So in your programming assignment 3, what you would do is that you would actually train a model like this on your favorite data set, which is handwritten digits. And then you'll say, okay, given a new digit, is it digit 0, 1 through 9, right? So it's a very similar setup to neural networks, except you're using a different classifier now, right? In fact, just to give you a sort of some more intuition behind this, you can think of this whole logistic regression also like a very simple neural network. So think of it this way. So you have some inputs coming in. Let's say your data is d-dimensional, right? And then what's happening is that you have these k nodes. Let's say you have k output classes. So you have 1, 2, 3, 4 k, right? And in each one of these there resides a vector, w1, w2. This is very similar to neural networks. And then everyone gets all the inputs, right? And then what you do here is that you simply compute exp of w transpose x and so on, and then everybody computes this softmax output, which is exp w1 x over summation and so on, right? And that's it. So it's a very rudimentary version of a neural network. In neural network, you have another node here, and then things get combined and so on, right? But here, you just have this kind of combination. And because of this, if you apply multinomial logistic regression to any data, you will see that your decision boundaries are straight, they are linear, because W gets combined with X in sort of a linear fashion, and there is no activation after this, right? This is the output that you use. So that is why it gives a linear combination. However, you can always do basis function expansion if you want non-linear outputs. All right? Any questions? Now the next question is, how do we learn it, right? So there are two ways to learn this, and let's look at quickly the first way. One is what we call, and this is actually a general discussion, where if you want to learn K classifiers, let's say, if you want to learn a classifier which can distinguish between K classes, one way to train that classifier is that instead of that, you can pose K problems of one versus rest, all right? So that's called the one versus rest philosophy. So let's say you have K classes. I'm just going to denote them by these bags. So this is data for class 1, data for class 2, data for class 3, let's say 4. So K equal to 4 here. So this contains training data for class 1, 2, 3, 4, right? So one way to train this classifier would be that you create one problem in which you call this as your one class and the rest of it as another class. Okay, so you artificially create a new training data set in which all the data points that were in class 1 are labeled 1 and all rest of them are labeled 2, right, or something else. And then you train a binary classifier like a logistic regression, binary logistic regression, because we know how to do that, right? So you'll get one classifier. So you'll get one classifier which does 1 versus 2, 3, 4. Then you train another one which is 2 versus 1, 3, 4, 3 versus 1, 2, 4, and 4 versus 1, 2, 3. Right? So you can learn these 4. These are all binary. So we know how to do these, right? And then what you do is, when you get a new data point, right? So you feed it to each one of these classifiers, right? And each one of them will give you a probability, right? It's a logistic regression, binary logistic regression. So for a new data point, you'll get 4 probabilities, and that's it. Then you choose the one that is highest, right? So that is one way to do this, learn these weights. Each one of them will give you some weights. Another approach is what we call one versus other, in which instead of training 4, you will learn actually 4 choose 2 classifiers. You'll choose a class. You'll first train a classifier. So that's one versus rest, right? And then another approach is one versus other. And here what you do is that you'll do 1 versus 2, 1 versus 3, 1 versus 4, right, and so on. So you'll take every pair and you learn a classifier for each pair. And then when a new data point comes, you will feed it to all of them and figure out which one is the highest, right? So there is some post-processing involved here. So that's one versus other. And there is no real sort of theoretical guarantees about which one is better over another. This is more like just a heuristic. You can think of these just as heuristics, right? You didn't have any other way to do it, so this is how you do it. Of course, one thing you can see is that if you go one versus other route, you will have to train many more classifiers, right? And so if your number of classes is very large, then it becomes a little more ineffective. If you're going one versus rest, then you always have to train K classifiers. But then there are other issues as well. For example, let's say if you took this, right? So in this data set, the number of samples from class 1 will be much smaller than everything else. So it will be kind of imbalanced, and you might lead to some issues there. Here, things would be more balanced if your classes are balanced to begin with. So there is, pros and cons. So, but this is sort of a general, simpler way to do things. In fact, for your third programming assignment, you would be doing one versus rest training, which will be sort of one way to do it. However, for multi-nully or multi-class logistic regression, you can actually learn all those weights directly instead of doing this business, right? So the way to do that would be, and in fact that's something that we'll not quite talk about here, but if you think about this, right, since you're assuming that p y given x is a multi-nully, right, which means that you can write the probability for every class, which means you can compute the likelihood function, right? You can compute the likelihood for all data points, which will be kind of a variant of what we did here, except that instead of having just one class, this will be yi log theta I plus y1 log theta 1 plus y2 log theta 2 all the way to yk log theta k, where each theta k will be exp of wk transpose x over that summation term, right? So but the point is that you can compute the log likelihood, and once you know log likelihood, you can do the gradient descent way, or you can incorporate the Newton method by computing the Hessian. So you can do everything, right? So it's the same principle applied to a slightly different likelihood function. Okay, so I don't know if let's see. Right, for your third assignment for the extra credit, I think you'll have to do that, right? And then we can discuss it a little more. But for rest of the discussion here, we are not going to focus on how to directly learn the K-class logistic regression, okay? Any questions? Cool, all right. So that is one part that I want to talk about logistic regression. And the next part that I want to talk about is a little more advanced in some sense. Some of you might just groan saying, hey, here we are back at it again. But I just want to talk about it because it kind of completes the picture about the discussion. But for your assignment or for an exam, we won't really be using it anymore. Right? So of course, I don't know if I told you before, but I'm a strong Bayesian person, right? So which means that when we do these parameter estimation, I want to get some posterior on my estimates, right? Remember, in Bayesian setting, we are not just happy with computing our MLE, right? So this you can think of the W that you learn here after updating all your weights is MLE, because you are trying to maximize your likelihood or log likelihood, right? But what if I want to do Bayesian logistic regression, right? Which means that I want to start with some prior on W, which will be, of course, this W is a vector, so most natural prior is a Gaussian distribution. And then I want to reach a posterior, right, of W given D. And then I want to use either the map of that posterior as my W, or I want to do my favorite Bayesian averaging over all possible Ws and work with that, right? So if I want to do that, the problem is that this whole business is not as straightforward as what we did when we did what do you do? Linear regression, right? So in linear regression also, we looked at Bayesian linear regression, where we said, let's put a prior on W, which will be a Gaussian prior, and then compute the posterior of W. And we were actually able to compute the exact posterior. In fact, it turned out that the posterior of W will also be a Gaussian, right? And the reason was that because the prior is Gaussian, and your likelihood function is also Gaussian. Remember, y is also Gaussian with respect to W transpose x, right? Which means that the posterior, and Gaussian is a conjugate of itself, which means that your posterior will also be Gaussian. So if you recall, this was the exact same logic that we used when we were trying to estimate the posterior estimates for a coin parameter, right? Where we said, let's start with a beta prior on my theta, and since my likelihood is a Bernoulli distribution, and Bernoulli and beta are conjugates, that means my posterior was also beta. So that was all nice. But here things become a little different. We start with a Gaussian prior on W. However, my likelihood of y is not Gaussian anymore. My likelihood is actually multi-nully or Bernoulli, depending on what the problem you're looking at. Let's look at two-class problem. So our likelihood is Bernoulli. Our prior is Gaussian, and they are not conjugates of each other. So there is no way you can get a direct form for your posterior, right? So just mathematically, if you want to look at this problem, so here is the problem. So what do we do in Bayesian regression, right, or Bayesian logistic regression? We want to start with a prior on W, right? And let's say this, and since W is a vector of any kind of values, that is the most natural is some Gaussian prior, right? In fact, we are going to assume that this is 0, just like we did for linear regression. So basically what we are saying is that without seeing any data, I assume that my weight vector is a Gaussian random variable centered at 0 as the origin with some covariance matrix, right? So that is the idea. And then we compute the likelihood of my data, which is nothing but just a product over all my training instances, P of Y, right, given X and using the W that we have, right? So this, of course, we said that this is a Bernoulli distribution, right? Now we want to find the posterior for W. So let's call this data as D. Posterior. So this is P of D given W is equal to this, right? This is all of my data. And find the posterior for W, which is P of W given D. So now I want to flip it. How do I revise my estimate for weights after observing all the data? So this is going to be a simple application of Bayes' rule, where we say this is equal to P of D given W times P of W over an integration, because W is going to take infinite possible values, right? So instead of a summation, this will be integration. We have seen that before, right? Now we know all of these things, right? It's not like we don't know what these things are. So we can substitute it here. These are just mathematical functions. We don't have to be scared of these. Yi, right? So this times P of W, also we know it's going to be a Gaussian. So whatever is the Gaussian expression, if you remember it, 2 pi tau. Right? Because the mean is 0. That's why there's no minus mean. And then I didn't expand this, but you know what this is, right? This is just theta I, whatever about that. And then integration of this whole thing here, right? Now the thing that kills us when we have to compute this PW given D is this integration, right? Integration is hard, right? Any mathematician will tell you that I can do differentiation, but integration gives us nightmares, right? In particular, when your functions are such complex functions of W, right? Things are, of course, this is fine. This is an integration that we always know. E of exp of x dx integration is exp of x. That's why Gaussians always are nice to work with. But this is the part, and especially when it gets multiplied with this, is that just goes insane. Because remember, this, the likelihood of yi given xiw is yi raised to power theta I times 1 minus yi raised to power 1 minus theta I. And the w is inside that theta I, right? So it is in the raised to power hidden inside an exponent, right? So just crazy. So that's why computing the posterior is very hard, okay? So in fact, writing this itself is a pain. So computing PW given D is hard. Okay, put extra emphasis. And that is why whenever things are conjugates of each other, because if there's a function, that is what we mean by conjugate. What happens with conjugates is that this function, when it multiplies with this, it actually makes the function simpler, and then we can compute the integration. So that is all what conjugate means. So conjugate means that you are able to compute this easily. But if it's not a conjugate, then can't do anything, right? So now how do we compute this? Right? So that is what we call, can we compute an approximate posterior? That is the question. So we can't compute the posterior because we are not evolved enough to solve these hard integrations. Maybe generations down the line we might be able to do that, but right now we can't. Which means that we cannot compute the exact, or let's say computing exact PW given D is hard. Can we compute an approximate posterior? So that is actually a whole line in machine learning. So if you are interested in research in machine learning, this is something that you will do over and over again. That you would, it's easy to formulate problems, right? It's very easy to say, okay, y is this distribution, x is this, and so on. The problem comes when you have to compute these posteriors. When you given something, approximate the other thing, because of this integration, right? Of course, Bayes rule is applicable everywhere, but Bayes rule stops here. After that, you have to compute this value, right? And depending on what this is here, it might become very hard, and that's why people, instead of that, rely on computing approximate posteriors, all right? So today I'm going to give you a very quick sort of a sketch of how we do it for logistic regression, but same philosophy can be applied other places as well. Okay. So one thing before that is that if you remember, too much of dancing around here. When I talked about this, right? So when we did this regularization, essentially what we did was we applied some Gaussian prior to W, right? So this is exactly like Bayesian logistic regression, linear regression, is that when we applied this prior, we can get the W which maximizes that regularized likelihood, which is kind of like the posterior, right? So which means that if you solve this equation, it will give you, or if you sort of feed this to your gradient descent optimizer, it will give you an estimate for W which incorporates the prior, right? But this will give you the maximum value, which means that you can get the map of W, okay? So that is the main point I want to make, is that we can compute W map by optimizing the L2 regularized likelihood, right? The place where we added a lambda W transpose W prior onto or a penalty on your likelihood function, right? So you can compute the W map, but we do not have this. So it's like there's a distribution, and I don't know what the form of the distribution is, but what I have is the maximum value that distribution takes, right? So now can I approximate what my distribution would be given this information, right? So this is what I do in these slides. So we quickly go through that. Right. So this is a little more involved. So I'll just go through it, but if somebody is interested, we can talk about it in more detail in my office hours. So what we do here is we assume that our posterior has this form. So that is the first approximation I make. I'm not really making any assumptions about what form it is. I'm not saying that PW given D is a normal distribution, which I would be tempted to do. All I'm saying is that it has this form. There is some constant term here, some normalization term, and there's an exp term raised to some energy function, E function of W. So there's some function here, right? And typically we say this is the energy function. All right. So we assume this is the form. Then what we do is we say that, okay, we know what the map is, right? Whatever this distribution is, I know what is the map. Now I want to go back and say what is W, P of W given D. So what I do is we do this Taylor series expansion, which is just an expansion of a function around the maximum value, right? So if you remember your calculus classes from I don't know how many years ago. For me, it's going to be 20 years at least. But if you compute this Taylor series expansion, which is saying that f of x, or e of w in this case, is e of w at the maximum value, right, plus the difference, I don't know why there's star, this should be map, difference times the first derivative plus the quadratic difference times the second derivative plus third derivative and so on, right? That's the Taylor series expansion. The idea is that f of x can be written as so in a single variable case, Taylor series expansion goes like this, right? So if I have f of x, I can write it as f of x naught at any x naught plus x minus x naught times f prime at x naught, right, plus x minus x naught square, and there's a 1 over some factorial stuff that starts coming in, f x naught plus so on, right, so till infinity. So this is what Taylor said, that you can approximate a function, well, actually you can expand a function at any value like this, right? So the equation that you see on the slide is just a generalization for a vector case, where you instead of x you have a vector w, but you can expand it like this. And typically what people do is that if this difference is not too large, then you can ignore the higher order term and just look at the first two. You'll say e of w is nearly equal to this plus the first order and the second order term, right? And of course, since we are computing this, so we know this is the gradient and this is the Hessian, right? Second order. All right. Now what we do is, since we are assuming that your w is the second term is w map, so that's a mode, right? So at the mode, we know that the gradient is 0, because at that point, mode is where the function takes the maximum value, right? So w map, the gradient term will vanish, because the gradient at w map is going to be 0, right? So we'll be just left with this part. So e of w is nearly equal to the e of w at map plus this term. This should be w map, I'll fix it later, but essentially this, right? So now if you fit that, right, if you feed this into your approximate function, remember this, right? So here, instead of e of w, I'll replace it with e of w map plus w minus w map h w map, w minus w map, which is here. Then you can rewrite this whole term like this. So there'll be 1 over z times some constant term here times this. And then suddenly what we do is we make this jump, saying, hey, this looks like a Gaussian PDF of a Gaussian distribution. And so then what we assume is that the posterior for w can be approximated as a normal distribution centered at your map, and the covariance matrix is given by the inverse of your Hessian. All right. So this is a little sort of a jumpy discussion. So I can explain it in more detail if somebody is interested. But the main point I'm trying to make here is that there are ways to approximate the posterior without really trying to solve that scary integration at the bottom. And the general recipe is this, that you assume certain form of your posterior, and then you do this Taylor series expansion around the mode that you know, and then typically it comes out to this. So essentially what it shows you is that the posterior approximately is a Gaussian distribution with centered at the map that you can compute using your regularized likelihood, and the covariance matrix is given by the inverse of the Hessian at map. Okay. All right. So that is the idea. So of course this was a discussion that I was trying to tell you earlier, is that if you want to exactly compute the posterior, it's very hard, because you have to do this business at the bottom. All right. So that is the idea. Approximate posterior is given by this. Any questions so far? Yes. So over here, the z. Over here. Yeah. So here what we do is, the reason we made a jump from here to here, this is the approximation we did. We said we'll assume that this part just computes to 1 over 2 pi, whatever, So we don't really actually compute this z. We just assume that this whole quantity over here, this constant quantity, is going to be same as 1 over 2 pi d by 2 determinant of this H. So this is the approximation. This might not be true, but since we are so into approximating it as a multivariate Gaussian, we kind of assume that this will be equal to the term that we need for a Gaussian. So we don't really compute. Any other questions? What is the time? I think we're out of time. All right. So next time I'll show you how to now use this posterior to do the Bayesian inference, right? So you can use this posterior in two ways. One is you can use the map, but that is same as using the map earlier, right? That doesn't give us any benefit. But you can use this posterior in a Bayesian averaging way, where you take every possibility for W and then multiply it with the probability. And we'll see how to do that next time. That will be maybe like a 5-minute discussion, and then we'll move to support vector machines.